All right, I've got the recording started. We've got lecture slide up. Can somebody let me know just again to make sure that the slide's showing up good and everybody can see and hear me?
I can see
Yeah,
the
I can see
slides.
everything.
Oh, I see everything.
Good deal.
Thank
All
you.
right. Well, everybody, welcome back to Structural Analysis. Hopefully everybody is staying dry out there. It's a pretty rainy day out there today. I wanted to begin by discussing a few quick announcements. So first off, the attendance grades are up to date as of today on Blackboard. Typically what I will do is I'll try and update them once a week. Again, what I do is I just use the logs from the time that you've logged into the Collaborate session. So I probably won't do that after every lecture, but my goal is once a week. Every now and then, if I have time, I might just go ahead and update them while I can. I also want to make sure that everybody's good on the homework schedule, because this is probably how it's going to be for a little while. So you all turned in a homework assignment on Friday. I have graded that assignment. The grades are posted along with the solution. And so homework 1 is sort of taken care of. Now, homework 2.1 was due at 10 a.m. this morning. So hopefully everybody has submitted that. I looked and most people had already submitted that prior to class. So homework 2.1 is already submitted, or that you've submitted it. I'm going to have that graded between now and Wednesday. And then after class today, you'll have an assignment that will be due on Wednesday at 10 a.m. And that'll sort of be the cycle that we engage in for the next, probably few weeks, is that every day you'll have an assignment due before class and an assignment after class. And again, the idea is that they're not going to be terribly long assignments, that they're going to hopefully be pretty manageable. And so that's what we're going to do for the next few weeks. I'll go ahead and mention one other thing. I'm going to tweak the lecture schedule a bit. I know we were only supposed to have 3 days on reactions, but I think I'm going to do 4 days on reactions, because I think by covering a couple of the topics a bit more in depth, it'll make our coverage of shear and moment diagrams later a lot smoother. So I decided to call a little bit of an audible on that. Everybody good? Any questions about what we talked about up until now? Anything about the announcements before we go ahead and get this started up? All right. Okay, so what we're going to do today is we're going to continue our discussion with support reactions, and the idea behind the next few lectures is that what we're going to do is take what we did last time and just build on it a little bit, just add a little more. Last time, let's go back to what we talked about last time. So last time, what we did is we started our discussion of support reactions, and really what hopefully we can handle by now, after the homework that you had this weekend and what we did in class on Friday, is that you can handle some pretty basic problems. We have yet to deal with a fixed end, the boundary condition on the bottom, but that'll be what we deal with on Wednesday. But you can handle simply supported, overhanging conditions. You can handle concentrated loads, and you can handle distributed loads, whether or not they are a uniformly distributed load like what you see on top, or whether they're a triangular or a linearly distributed load. And so what we're going to do today is we're going to take that and we're going to build on it by adding another little variable into the mix. And we're going to keep doing that, and by the time it's all said and done, we'll pretty much be able to handle just about any structure that I throw out at you, and that's kind of the overall point. So what we're going to do today is we're going to take those loads and we're going to place them at an incline. So how do we handle an incline loading scenario? Okay, so keep in mind the loads don't have to be always going up and down. Sometimes they can be going to the left or to the right. Now we can define that by one of two ways, either by the angle at which the load is oriented, or by the slope ratio. And I'll go ahead and tell you, in structural engineering, more often than not, we define things by slope ratios than we do angles. So, and the reason for that just sort of goes with the way that we draft engineering plans and the way that we fabricate things. So for instance, if I have a truss, as a fabricator and as an erector, I almost don't really care so much about that angle of let's say a given diagonal member, as much as I care that it's so much long and that it, so much rise over so much run. And so when you're drafting that out, in an engineering drafting standpoint, you're really going to be specifying more rises and runs than you're going to be specifying angles. And so more often than not, we specify our inclines or our diagonal components in this course with slope ratios. It also actually, in my opinion, makes the math a little bit easier because you can just use SOHCAHTOA to determine your X and Y components. Which, speaking of, that is the easiest way to handle incline loads, or as we're going to see here in a second, incline reactions, is to split it up into its X and Y components. So, for instance, if we take the image on the top of the slide, I have an angled load that might be something at like a 3 to 4 slope ratio or a 1 to 12 slope ratio or what have you. And so I just use SOHCAHTOA to say that the X component is the force times H over R, the horizontal leg divided by the hypotenuse, and then the vertical component is times V over R. And we're going to do that quite a bit. Now, I'm sure there's going to be, excuse me, my Jolly Rancher's getting to me. I'm sure there's going to be a couple of people in here that are going to be more comfortable with the trig. And also, we are going to have some problems that are going to be specified by an angle. You can always split that up into its components just using sines and cosines. Just always be really careful when you're using the trig functions, especially the angle. What I have here on the slide is I have the X component as defined as the force times the cosine of the angle, and the Y component defined as F times the sine of the angle. But that only works when you have the angle referenced from the X axis. If it's referenced from the Y axis, then that doesn't work. So just be careful with that. Okay. Any questions before we just jump right into our first example? All right. So let's go ahead and get right into it. This is going to be the first example that we work on. Notice how it's got components from what we did last time as well as something new, and that's going to be kind of how I build a lot of examples. So we have a distributed load, but we also have a concentrated load, but it's at an angle, and it's at a 3 to 4 slope ratio. So we have a distributed load of 1.4 kips per foot, and then we have this angled load that's 20 kips at a 3 to 4 slope ratio. Simply supported boundary conditions. We're going to determine the support reactions on this beam. So let me go ahead and first off, let me share my my screen. Let me stop this share. Here comes the cascade. Yeah, for some reason, Blackboard doesn't like to share OneNote. Not sure why. Okay, let me move my keyboard out of the way. And then let me fold this down. Okay, so again, make sure everybody's aware that I'm doing these calculations in the course notebook that's on Microsoft Teams. So everything that I'm writing here on the screen, you'll be able to access. If you go into the notebook and go into content library, you'll see all these computations. Okay, so here's my my problem. Let's go ahead right off the bat and specify some things that we know just square one. First off, we have a roller here on the right, and so I'm going to assume that this reaction is upward, and we're going to call that By. And then we have this hinge over, or this pinned support over here on the left, and so it's going to have a vertical and a horizontal reaction. Let's go ahead and assume that, I can do better than that. Let's go ahead and assume that both of those reactions are upward. We'll call that one AY as well. And now for the horizontal reaction, what I'm going to do is I'm going to assume that this acts to the right. Okay. Now, here's the thing. I'll go ahead and tell you that assumption is wrong. It actually doesn't act to the right. It actually acts in the opposite direction. But I do want to have a problem where we go ahead and just make the wrong assumption, because I want you to see what happens, in practice if you assume that it acts one way and it doesn't. And the reason why is because on your homework assignment, I believe it's problem 2. There is I think it's 1 or 2. I'm pretty sure it's 2. But there's a situation where you kind of have to guess at the beginning whether or not it's going to be to the right or to the left. And it's possible that you guess incorrectly, and it's okay if you guess incorrectly. I want you to see what happens. Okay. All right. So with that, let's go ahead and keep on trucking. Now we have this distributed load. It's 1.4 kips per foot over a distance of 10 feet. So remember, I can idealize that as a single load of 14 kips. And we'll say that this dimension on either side is 5 feet. Okay. Now, so up until now, everything that we've been doing should be stuff that you're fine with, because we did this on Friday. You all did this on your homework assignments. This should be old hat at this point. Now let's deal with the new stuff. So we have this 20 kip load, and it is at an incline. Now, the way that this incline is specified is through a slope ratio. So we have a 3-to-4 slope ratio. Now, just to make sure everybody's paying attention, let me ask chat, if the legs of this triangle are 3 and 4, what's the length of the hypotenuse? Good deal. Exactly right. So yeah, 3, 4, 5 triangles. I'll go ahead and tell you they're going to pop up quite a bit in this class, and some of those, those Pythagorean triples. What is it, like 8, 15, and 17, stuff like that? They're going to pop up a bit just to make some of the computations that we do a bit easier. So I just wanted you to be aware of that. Okay. Now, what I'm going to do over here off to the side is I have a 3, 4, 5 triangle, and I have this 20 kip load. Was there a question? No. Okay. I have a 3, 4, 5 triangle, and I have this 20 kip load. What I'm going to do off to the side is I'm going to go ahead and compute the x and y components of that. And the way that I'm going to do that is I'm going to say 20 kips times the ratio for each leg of the triangle. So that would be 3/5 and 20 kips. All right, I'll just keep that shorthand. 20 kips times 4/5. Now this is pretty simple. 20 kips times 3/5 is 0.6. 20 times 0.6 is 12, and this is 20 times 4/5, which is 0.8. 0.8 times 20, it's 16. Okay. So I've got 20 kips that can be split up into its x and y components of 12 kips and 16 kips.
Excuse me. So is
yes, sir.
12 kips the x component, or is it the y component?
That's what I was getting ready to go through. I'm glad you brought that up. The way that you assign this, it's really, really easy. All you do is you look at the triangle and you ask yourself, for instance, I have a 3, 4, 5. Which is the biggest leg? Is it the vertical leg or is it the horizontal leg? And the biggest leg is the vertical leg. So because the biggest leg is the vertical, we put the biggest component going vertically and the smallest going horizontally. And so basically all you do is you just assign the component that goes with the appropriate scale. So if the smaller component is the vertical component, then you put the smaller component going vertically, and it's pretty much that simple. And I want to make sure that is very clear. Is everybody else okay with that? Are there any questions on that? That was perfect timing on your question. Okay. All right. So if you're okay with that, so if you have an inclined load and you have the ratio defined that way, that's how you would split that up into its x and y components. Now we can go through and start chugging this out. Okay, so let's start off. Let's do this problem the exact same way we did the problems last time. We'll start off by summing moments at A. And we're going to go through this in the exact same process. Okay, so starting off at A, so start all the way at the left and just work your way across the structure. So AX and AY, we don't have to consider those because they go right through A, so the moment arm is 0. But we do have to consider the 14 kips. So 14 kips, does it go on the left or the right side? Now you can use your microphone if you want. Left, there we go.
Left side.
There we go. And what's the moment arm?
5 feet.
5 feet, there you go. Okay, now, so we've taken care of AX, taken care of AY, taken care of our 14 kips. Now, what about the 12 kips and the 16 kips? Okay, let's take each of those one at a time. Do we consider the 12 kips?
Oh, it goes through point
its
A.
line of action goes through the point.
Exactly right. So we can neglect the 12 kips across the board. Okay, what about the 16 kips? If we neglected the 12 kips, do we have to consider the 16 kips?
Yes, we consider the 16 kips.
Yeah, exactly right. Left or right side?
Left.
Yeah, it'll be left again.
There you go. 16 kips. And what's our moment arm? $18 feet. There you go. All right. And lastly, so we've taken care of, and so now that we've taken care of our incon load, this problem is no different. And that's sort of one of the mistakes I want to try and break down, is that while the problems look more complicated and they get funkier, they really don't. It's all the same stuff. So if you get to the point where some of these problems feel like you're getting bored, then that's probably a good thing, because then you know how to do it. That's kind of the point. Now BY, I'll go ahead and tell you BY, we're going to put that on the opposite side because it's going upwards. And our moment arm, it's pretty much spelled out for us down here on the bottom. That's going to be 24 feet. And so that's basically it. Now, over here on the left, let me walk through some of that math. 14 times 5 is 70. 16 times 18, that's 288. And so 70 plus 288, that comes out to 358. And again, that's my little shorthand there for foot kips, equals BY times 24 feet. And so BY equals what? Somebody help me out in the class. What's BY going to be? We know it's going to be positive, but
It has multiple decimal points, but rounded to the last 2 decimal places, 14.92 kips.
There you go, exactly right. And for the purpose of that brings up a great point. This is structural engineering, so this is real life, and in real life you're going to deal with real life numbers. Sometimes the problems that we do in class, the answer will be 10 kips, and sometimes it will be 18.63428 whatever kips. If you're rounding your answers to like 2 decimal places, that's good enough. I mean, a lot of times what we do in structural engineering is we break out an engineer's favorite tool, which is Excel, and it does a lot of the math for us. So a lot of times rounding and even significant figures ends up not really accounting for much in our designs, just because what we do is so large scale. But for the purposes of the class, if you're to like 2 decimal places, that's going to be good enough. So that's 14.92
Yeah, just based on my
kips.
experience reading structural design drawings, like that's pretty precise for what they should.
You're right. In fact, a lot of times on drawings, you'll see to the 10th of a kip, or maybe even just to the even kip, depending upon the project. And again, I'm of the opinion that once at that point, we're not arguing over whether or not the process is correct. We're arguing about plus or minus 10 pounds on a column that could see hundreds of kips. It ends up not mattering. So.
Just a quick side note here before Well, eventually on the horizontal forces, we may have to reassume our AX because
No, I know, and that's a great point. So I'll go ahead and tell you, I purposefully assumed the incorrect direction, and I did that for a reason, so that because on your homework assignment there are some situations where it might not be so clear, and you're going to have to make a guess, and so I want to go through a situation where the guess was wrong, so that everybody's sort of clear on how that would happen. So that was on purpose. This is great stuff, and again, like if you got questions, don't hesitate. I love this stuff. All right. Everybody good with me so far? All right, let's keep on trucking. We're going to do sum of forces in the y direction now, and we could do sum of forces in the y direction or the x direction at this point. It really wouldn't matter. We can go up, we can go down. And so you just start listing everything's going up and everything's going down. Just start at the left, work your way across. So AY, we have that drawn upwards. 14 kips, we have that downwards. 16 kips, that's downwards. And then BY is upwards, but we know that's 14.92. And that's basically it. So AY plus 14.92 kips is 14 and 16, that's 30 kips. And so if we chug that out, so 30 minus 14.92, that's easy. I'll just go ahead and put that here. That's 15.08. So positive 15.08, which is 15.08 kips going up. All right. Everybody good? Okay. Now let me go ahead and do sum of forces in the x direction, and let me make the screen bigger. I don't want to keep going back and forth, so maybe that'll help us out a bit. Okay. Now up until now we've really just sort of said sum of forces in the x direction is 0, and we've just looked at it and said that the reaction is what it is. Now I'm actually going to draw out the table. And so we'll put everything on the left and everything on the right. So let's chug this out. So when I look at the structure, I have AX drawn on the right, and I have 12 kips on the right. And I don't have anything on the left. There's nothing here on the structure that's pointing to the left. So what I'm going to do is I'm just going to, keep along with my assumption. So 0 equals AX plus 12 kips. Now, just look at this equation. 0 equals a variable plus 12. What's the variable? Well, when I solve this out, I get that AX is negative. See how on all of these previous scenarios, so like BY is positive 14.92 kips. AY is positive 15.8 kips. I'm doing that to sort of indicate to myself that I assumed a direction, and this is the statement that proves that assumption is correct. Well, now I got a negative answer, and what that means is that my assumption was incorrect. I assumed that AX was acting to the right. I was wrong. That means that it is in fact 12 kips acting to the left. Okay. And while it's pretty easy to just look at this structure, I mean, you take a look at it, the only force on it was 12 kips to the right, so you had to have 12 kips to the left. But in some scenarios, it's not so easy because you've got a lot of different loads going, you've got multiple unknowns, and so you kind of have to just make a guess and go with it. If you get a negative answer, that's okay. You just make sure that you've got good bookkeeping and that you're tracking, what you assumed and what the answer came out to be. And that's sort of the nice thing, is that if you do the math correctly, the statics will bear itself out. So to summarize, AX is 12 kips to the left. AY is 15.08 kips acting upwards, and BY is 14.92 kips acting upwards. And so that is the answer.
Dr. Michelson?
Yes, sir.
Yes, sir. Just a curiosity question here, but why are you writing the K symbol where we would put power? I just
Oh, it's just my shorthand. I could put it. I could do 14.92 kips or 14.92 kips. Not really a reason. Just sometimes when I'm writing like a moment, like 250 foot kips, I put the two symbols next to one another.
okay. I was
Not really a reason. It's not an exponent. It's just there's not really a reason. I guess I would say.
I just thought I was wondering what was that about. Sorry.
No, it doesn't mean an exponent. It's just a shorthand way of writing it. You can write out the full kips if you want. There's nothing wrong with that. Do we always need to denote direction in our answers? I tend to only show it if it's counter to what's in my diagram. I would actually like you to get into the practice of doing that for a couple of reasons. One of the big ones is that later on, we're going to be dealing with problems where we have one structure. We have multiple load cases on that structure. So a couple of examples of that are when we do deflections, particularly using the principle of virtual work. So there's a real structure or a real set of structural loadings, and then there's actually a fictitious virtual set of structural loadings. And so when there's a couple of different load scenarios going on the same structure, sometimes I find it easiest to just make sure when I'm indicating that it's the answer that I put the arrows on there. Especially when you're making assumptions and then the assumptions are invalid. To me, I find that it reduces error across the board, that when you say this is the answer, that you write the numbers as well as the directions. It'll help you out in the end.
And for your answer that you have, is that how you want us to write it? Like all of them in line and then box it, not just like AX boxed, AY, and BY boxed, like separately?
That's a good question, and I'm actually fine either way, as long as it's clear that those are the answers. So, for instance, if you, let me stop the share here. So, like if you had, a problem and you had, AX is 12 kips here, and then you had AY is 15.08 kips here. If you box that and box that, like that's fine. I don't have a problem with that. As long as I don't have to go on a fishing expedition to figure out what the answer is. As long as it's clear, I'm easy to get along with. And one other thing I'll add to that how we denote our answer is going to change as we move forward throughout the class. For instance, when we draw shear and moment diagrams, the shear and moment diagram is the answer. So you aren't really going to have to box the whole thing and say this is the answer. I'm going to know that that's the answer. Whereas when we do trusses, typically what we'll do is we'll just redraw the truss and put the forces and the answers directly on the truss to make it easy to find. So that is going to change a bit, but the simplest answer is as long as it's clear to find, I'm good to go. This is great stuff. Any other questions? Okay. Now what I want to do is I want to add another little quirk into the mix, and I'm showing you this on the camera because I kind of want to make a point on this. Now, instead of talking about inclined loads, I'd like to talk about inclined supports, particularly or specifically inclined rollers. Okay, so for instance, let's say I have a structure. Okay, and can everybody see the board? Is this coming through clearly? I know I'm kind of probably in the way.
Yeah,
But
I can see it
can you
just fine.
see? Okay, good. Okay, so let's say I have the end of a structure. So this is the beam, it sort of goes on. And I have a roller here, but let's say, for instance, that I have the roller is on an incline. So, for instance, here's the roller, and the roller's actually like this. Whenever the roller is on an incline, what it means is that the reaction is going to be perpendicular to that inclined surface. But I want to show you something about how we address that. And the easiest way I can do that, or to explain it, is I want to show you an incline, but a very, very, very like shallow incline, one that's not steep at all. So let's do this, and let's say that, like I said, really, really shallow incline. Let's say it's something, like 1 to 12, So again, not very steep at all, okay? So you would probably agree with me that the ground is very horizontal. It just has a very light incline. So if I were to look at the reaction is going to be very, very vertical, okay? It's going to have a little bit of tilt to it, but not much, okay? So one of the ways we denote this is, so for instance, if this is support B, instead of calling this BX or BY, sometimes we'll just call it the reaction at B. Instead of trying to say, was it X or Y, we'll just do this. Now, here's the kicker, okay? Now, again, this ground it's very, very horizontal. It has a very light incline. So the reaction is going to be very, very vertical. Now, the way that we do this mathematically is if this is 1 to 12, this is, 12 to 1. We take the numbers and we flip them, okay? And that goes back to a principle that we use in math. So, for instance, if you have a line and you want to plot a line with a perpendicular slope, one where they intersect at 90 degrees, how do you do that? If you remember, there's a formula for that. The slope of the line perpendicular, you take the slope and you flip it. So if you have one line that's 2/3, then the perpendicular slope is 3/2. Well, it's -3/2, but again, the idea is that you flip the fraction. We do the same thing with the slope ratio here. So if this is 1 to 12, that becomes 12 to 1. So let me pull up my slide here now that I've sort of went through that, and let me kind of show you what I got going on here. So here's the slide, and I used another one of those, pretty triangles or special triangles. So you know how there's a 3, 4, 5. So you have 3, 4, 5. That comes out nicely. Another one that comes out is 5, 12, and then 13. That's another pretty one. So let's say you have an incline roller and the ground is on a 5 to 12 slope ratio, then the reaction is going to be on a 12 to 5. So you flip the terms, okay? So the 12 is now associated with the Y component, and the 5 is now associated with the X component. And again, it just goes back to that perpendicular line. I've been teaching this class for a while, and I know that sometimes is something that can come up with students. So I wanted to have a discussion just about this, and then in turn have a problem just about this, just looking at an incline roller. But is everybody good before we move on to this next example? And don't worry, if it's a little funky, we're going to do this together.
Give me a moment to write this down, please.
No worries, no worries. Take your time. And keep in mind, all the slides are uploaded to Blackboard. But I'm having no problem with taking a minute or two. Okay, good deal. All right. Are incline rollers actually practical in design? That's a good question, and I'll say this. I think it depends on the particular structure that you're assessing. Admittedly, it is fairly rare. I would say that more the point of what we're doing with this exercise and exercises to come is just to make sure that we're comfortable with incline loads in general. I'd say where this really comes into play is when we're doing truss analyses, because when you're looking at a method of joints analysis, you've just got incline loads coming in all over the place, and that happens all the time. The actual physics of an incline support doesn't happen very much, but analytically, it serves a benefit for us covering that later. To give you an example of something that we will see later, on Friday, we're going to be looking at internal hinges and structures. And to be clear, there are structures out there that do have designs that have, you know, a connection that can be idealized as a hinge. But nowadays, in a lot of modern designs, we're not actually placing a straight up hinge inside a beam. And so the question becomes, well, if we don't really do that anymore, then why would we even worry about analyzing it? And the answer is that while we may not physically in real life install a hinge, hinges serve as a really nifty analytical tool for later. For instance, when we draw an influence line, when we're drawing an influence line for moments, a really easy shortcut way of doing that is to install a hinge at the point where we want to draw the influence line. And that's something we'll talk about way down the line. That's like October, November stuff. But you're going to see how being able to understand how a hinge operates will really impact how we draw influence lines later. So some of this is practical and some of this is just developing the tools that we need later on. That's a great question though. And I always want to make sure that you all are thinking about this stuff, about where this stuff applies in real life. And I do my best to go through this and say, well, if it's not really applicable, I'm going to try and not spend too much time on it. All right, so let's do an inclined roller problem. Now this one, this is I specified it by an angle, and whether you specify it by an angle or by a slope ratio, the mechanics of what we do are going to be fairly straightforward and pretty much the same. So I have a beam, and then again, this is kind of a review of what we did on Friday. I have a triangular load or a linearly distributed load on this beam, and it's the only load on the beam. I wanted to keep this pretty straightforward and just make sure that we're clear with the roller. I have a roller, and it is at an incline of 20 degrees. Okay, so let's go back to the notes, or to the OneNote. Okay, now let me scroll over here a little bit. So here's the problem that we're looking at. Let me tilt my screen down again. I'm using my Surface, and I have to make sure I don't disconnect my mic and my camera and all that. Okay, so here's the problem, and let me move this over just a tad so I can draw some reactions on here. I'm going to be a little kinder on drawing the reactions in the correct direction. So this one we're going to have a y, and this one I'm going to go ahead and draw this in the correct direction, and I'll show you how I could arrive that it's going to the right when you look at the roller here on the left. Now, for the roller on the left, or sorry, the roller on the right. For the roller on the right, what I'm going to do is I'm going to assume that it sort of acts like this, and we're just going to call that RB. Okay, so again, it's not a BY or a BX, it's just a reaction kind of going in that direction. All right, and so ultimately what I want to do is I want to figure out what is this component and what is that component. Okay, now before I do that though, let's just make sure we're all comfortable with the triangular load. This triangular load, if I wanted to idealize that as a single point load, how much would the point load be? I'm going to ask chat for that. Or the mic, use your microphones, chat, whatever.
72 kips.
72 kips, that's exactly right. Actually, let me use a dotted line for that. So, and then this dimension here, what is this dimension? Yep, exactly right. This is 12 feet. All right. Okay, so now we need this X and Y component for this RB. And what I want to do off here to the side is I sort of want to look at this triangle. So this triangle here, let's take this triangle and let's say this is 20 degrees. Now, if that's 20 degrees, we know that this side is going to correspond to the cosine of 20 degrees, and this side is going to correspond to the sine of 20 degrees. Everybody should be familiar with that with basic trig. Let me move this over a bit. Move that over a little bit. Okay. Now, somebody help me out in chat. Let's take the cosine. Somebody give me the cosine of 20 degrees, and let's just make sure we're being specific. Let's do 3 decimal places, just so that we're able to track these numbers. So cosine of 20 degrees. Everybody got a number for me? Is that cosine of 20 degrees? You might want to check your calculator on the radians.
It is 0.940 or
There you go. Yeah,
0.9396. Yeah.
0.940. There you go. And then sine of 20 degrees. .342. There you go. 0.342. Okay, that's exactly right. And so now what you're going to do is, okay, I've got this sort of unit triangle where, you know, I've got the x component is 0.94 and the y component is 0.342. When I indicate my reactions, I'm going to flip, okay? So this one here on the bottom, this one is going to be 0.940 RB. This one is going to be 0.342 RB. Again, I flip for the same reason that I do this, because it's a perpendicular line, and so you flip the slope ratios to get that perpendicular slope. And so I have the vertical component as 0.940 RB, horizontal component as 0.342 RB. If you're good with that, let me sort of walk through, let me make this big. Let me walk through the remainder of this problem, because past this, it's pretty simple. What we're going to do is, just like before, we're going to sum moments at A. And so, just like before, AX and AY, don't have to consider that. They go right through the support. We do have the 72 kips. That's going to cause moment at A with a moment arm of 12 feet. And then for the reaction, okay, instead of dealing with RB, we deal with the components, the X and Y components. I don't need to deal with the X component because it goes right through. Instead, all I have is the Y component times a moment arm of 36 feet. So I can probably actually take that table and make it a lot smaller, because that's it. That's all there is. So 72 times 12, 72 times 12, that's 864 is RB times 0.940 times 36 feet. And then we just solve for RB. That's it. So what is RB? Somebody in chat help me out. $25.53. That's exactly right. Now, this is another reason why the directions are incredibly important, like actually indicating the directions, because you want to make sure that you know what you're talking about. What did we solve for? We solved for RB. We didn't solve for the Y component. We actually solved for the original RB. we got a positive answer, which means our assumption on RB is correct. So it's not up, down, left, right. It's actually that way. We assumed RB was going in that direction, and we got the right answer. So that's the answer for RB, that it's that up, left, diagonal direction. Now, when we solve for forces in the y direction, what we can do is we can say AY is going up, 72 kips is going down. As for the y component, we can say, okay, 0.940 RB. And what does that come out to be? If you track your decimals, it actually has an exact answer. There you go. Yeah, exactly. It ends up being exactly 24 kips. Because basically what you're doing is you're, multiplying by 0.94 and then dividing by 0.94, so it ends up canceling out. So you get AY plus 24 kips is 72 kips, or AY is positive 48 kips, which is 48 kips acting upwards. And so again, like I said, if you want, you can, let me do this. You can circle that answer and you can circle this answer. That's fine. I have no problem with that. And let me also say one other thing. I can do that better. Later on, like, just so everybody's aware, I'm being pretty hyper formal with everything right now, making sure that I'm writing out all of my equations and all of my expressions. But I recognize that later on, this is going to be pretty simple, okay? I'm looking at this problem, and I see I have 0.342 RB acting to the right. So AX has got to be 0.342 RB acting to the left. If it's simple, and you can just recognize, hey, I'm looking at the structure, AX is 0.342 RB to the right. I'm fine with that. You don't have to go through and write the elaborate calculations if it's that easy to determine by observation. If it's not, you kind of need to go through it and chug it out. But again, I'm not going to get nuts on everybody over format it. As long as you're documenting your calculations and it's right, I'm completely fine with that. So AX ends up being 0.342 times RB, which if you plug and chug should be 8.74 kips to the right. So maybe A and S. All right, I'll leave that up here for a second. While you all are copying that down, I want to see if there's any questions. I know I probably went through that end part a tad quickly, but I want to make sure that everybody's comfortable with what we did here. Any questions? All right, let me pull something up real quick. I want to show you the homework assignment. So this is the homework assignment that's going to become available here in a sec. This is similar to one of the problems that's in there's two problems. This is similar to one of the problems that's in the textbook, but the one that was in the textbook had some components. It had a concentrated moment that we haven't talked about yet, so I wanted to take that off. This is sort of a custom problem that I came up with, as well as this one down here. So there's two problems. that involved either incline supports or rollers. I want to say one thing about problem 2. Problem 2, I'll go ahead and tell you, has a little bit of a coincidence type of answer. As you're going through the math, you might find that 2 of the answers come out the same, but that is just a coincidence. As long as you're doing the statics appropriately, the answer will come out just fine. I just wanted to prepare everybody for that. So this one's a frame, so it's not just a straight up beam, but again, the problem isn't any different. We have a pin support here, an incline roller here, no different than any of the other problems that we've done. Any questions before we close it out? All right, so that one's going to be due Wednesday at 10 a.m. Again, all the homeworks are going to be due at 10. Wednesday, what we're going to do is we're going to continue our discussion on reactions. We've dealt with incline loads today. On Wednesday, we're going to talk about concentrated moments, if you have a concentrated couple at a particular point. And then from there, we'll discuss fixed ended beams, cantilevered beams. That'll be our discussion on Wednesday, but that's all I have for everybody today. Everybody stay safe, try and stay dry, and we'll see you on Wednesday.